This is problem 44 from the photon. In problem 44, photons are incident on a very thick, depleted uranium target. In part A, we want to find at what energy will the beam penetrate deepest into the uranium. Okay, so we have our equation, which is on page 13 of the textbook, and you can go to page 18 in the appendix to get the density for uranium. So rho is equal to 19.1 grams per centimeter cubed for uranium. We want to know at what energy will the beam penetrate the deepest. Well, it will penetrate the deepest when the cross-sectional area is the smallest. That will be somewhere around here. So first I would look at page 18 and go to the graph to see when the cross-sectional area is the smallest. So this is for total attenuation with coherent scattering, and it's going to be somewhere between 1 mega electron volt and 10 mega electron volts. You can see that here. So then we want to know exactly where. So we go to page 19, and I'm looking somewhere between 1 mega electron volt and 10 mega electron volts. So somewhere between here and here for total attenuation with coherent scattering. I want when this value is the smallest. So that would be the 4.392 times 10 to the negative 2. So looking in this column of numbers, it's at 4.8, then it goes down to 4.3, and then it goes back up again. This is at 4 mega electron volts. So from looking at the graph and the table, we get about 4 mega electron volts. It isn't exact because we're only going by 1 mega electron volt here. So it's not 3 and it's not 5, but it's about 4. For part B, at the above energy, what thickness is needed to decrease the beam intensity by 50%? So if I take this and rewrite it as the number of photons that are left at a distance x over n naught, this is equal to 50%. If it's going to decrease the beam intensity by 50%, then you have 50% of the photons left. This is equal to e to the negative sigma rho x. This is at the above energy, so at the 4 mega electron volts, to decrease the beam intensity. Decreasing the beam intensity would be total attenuation with coherent scattering, so that's everything. At 4 mega electron volts, that was the 4.392 times 10 to the negative 2, which we used for part A. So sigma is 4.392 times 10 to the negative 2 centimeters squared per grams, which, how about I just write that as 0.04392 centimeters squared per grams. Okay, so now that I have that, what am I looking for in part B? I'm looking for the thickness, so I want to find x. Well, I can do the natural log of both sides, so then I have the natural log of 0.5 is equal to negative sigma rho x. Sigma is the cross-sectional area, so that's 0.04392 centimeters squared per grams. Rho is the density, which we found in the appendix. This is 19.1 grams per centimeter cubed times x. Therefore, x must be equal to the natural log of 0.5 divided by 0.04392 centimeters squared per grams and 19.1 grams per centimeter cubed. Grams cancel out. Centimeters squared here cancel out with all but one of my centimeters there. The units will be in centimeters. Since the natural log of 0.5 is negative, this will give me something positive. The natural log of 0.5 is negative 0.6931. My denominator is negative 0.8389. This gives me 0.8262. The units in the denominator were 1 over centimeters, so this is in centimeters. So that's part B. In part C, we are asked, at the above energy, which is the 4 mega electron volts, what is the dominant photon process? What percentage of photons undergo this process? Okay, so first, let's look at the graph. So 4 mega electron volts, that was somewhere between here and here. The dominant process, so this is not everything, this is just one process. The dominant process is this dotted line here, which is the highest between this point here and this point here. That dotted line is for incoherent scattering. So as long as 4 isn't before where this line becomes the highest, it's going to be incoherent scattering. So let's just double check in our table here. For 4 mega electron volts, we said incoherent scattering. So that means this cross-sectional area should be the largest. This is to the negative 4, so it's not that. This is the negative 3, so it's not that either. This is negative 5. This is everything. So we're just looking for one of these processes here. So ignore the last two columns. So I have 1.877 times 10 to the negative 2 and 2.236 times 10 to the negative 2. So this one's larger, so it must be incoherent scattering, which is the dominant process. I think I want this cross section as well. So for incoherent scattering, my cross-sectional area is 2.236 times 10 to the negative 2 centimeters squared per gram. And remember that incoherent scattering is Compton scattering. So incoherent or Compton scattering. I have my cross-sectional area and I want to find what percentage of the photons undergo this process. Well, I know how to do this. It's the same thing that I did in the previous problem. I take my equation here. If I want the percentage, that's the number of photons left over n naught. This is the percentage that is left. So if I want the percentage that undergoes the process, it'll be 1 minus this. So I'll do that afterwards. Okay, so this is e to the negative sigma rho x. So at 4 mega electron volts, I have 2.236 times 10 to the negative 2 centimeters squared per grams times rho, which is 19.1 grams per centimeter cubed, times x. What is x supposed to be here? Oh, that is what I found in part B. So this is 0.8262 centimeters. So E is, well, I don't know what it is. This whole thing is 0.703. So this is 1 minus 0.703, which gives me 29.7%. So that is the percentage of photons that undergo this process. So 70.3 are left, 29.7 undergo Compton scattering. So that concludes 44. And next we're going to look at problem 46.